The broadcast is now starting. All attendees are in listen-only mode.
Hello everyone, I would like to start this webinar session. I am Hideyuki Terashima from the University of Illinois, and I will be moderating this month's Joint Centers webinar. This webinar provides an opportunity for Center students to present about their research. To go over logistics, we will have two presentations this session. Each presentation will be 15 minutes long and will be followed by a 5-minute Q&A session. Please feel free to ask questions anytime using the chat box feature on the GoToWebinar app. This webinar will also be recorded and posted on the drinkingwatercenters.net website after the presentation is over. Our two presenters today are Deanna Ringenberg from the Nebraska Department of Natural Resources and Nicolas Beauchamp from Laval University. So at this point, I will start Deanna will be starting her presentation. So I will give her screen controls. And Deanna was formerly a student at University of Nebraska-Lincoln and is currently at Nebraska DNR. She will be going over the difficulties of implementing innovative technologies in small systems due to regulatory barriers and a survey she conducted to identify these barriers. Deanna, you can begin whenever you're ready.
All right, thanks for the introduction. Like I said, my name is Deanna Ringenberg, and this was my thesis topic. I graduated in August, so pretty exciting. Let's see, how do I advance? There we go. So I'm going to go over small and large systems, and then I'll move into regulatory compliance in the United States, new technology approval, and then we'll talk about a survey and the results and conclusions from that survey. So small systems in the United States make up a relatively small portion of the population. So you see, let's look at the pen. So only 24 million people are served by a small system. And for the purposes of this presentation, we're calling a small system less than 3,300 people. So we have 4 different population categories here. And as you can see, we have 24 million people, and the number of systems in the United States is 42,000. And we're just talking about community water systems. So as the systems get bigger, it's a smaller number of systems, but they're serving a larger amount of people. So here we have small systems aren't necessarily getting much attention because they're not serving that many people, but it is a lot of the infrastructure in the United States. Small systems tend to use groundwater as their source. As you can see here, blue is groundwater and green is surface water. So as our systems get bigger, they tend to use more surface water. Because the sources are different between small systems and large systems, we wanted to look into MCL violations, maximum contaminant level violations. Overall, we found that those violations occur with similar frequencies in all of the sizes. There was a slightly higher nitrate violation level for small systems. And that makes sense because nitrates are usually associated with groundwater. And as we said before, small systems tend to use groundwater. Disinfection byproduct MCL violations are usually associated with surface water. So we wanted to look a little bit deeper into systems with surface water. So we looked here. Here are the DBP disinfection byproduct stage 1 MCL violations. Here we have for all community water systems. And then we have surface water only systems. And then we wanted to look at purchased surface water systems, thinking that maybe they would have a higher disinfection byproduct MCL violation. We found that the percent of systems for purchased water systems, it's a very similar, it's actually lower than for all surface water. And there is a slightly higher disinfection byproduct violations for small surface water plants. But as we said before, most small systems are using groundwater. So in the United States, regulatory compliance starts with the EPA, with the Safe Drinking Water Act. And the EPA gives the states, the 49 state agencies, control or responsibility to make sure that all of the communities within their state are in compliance. And the reason why there's 49 is because Wyoming does not have a state agency that regulates drinking water. And the reason why it's set up like this is because states really want to make sure that drinking water from their state is in compliance. And America's a really big country. Things can really vary from state to state. And water quality, if you imagine, in Alaska is going to be a lot different than water quality in Louisiana. And each state, it's really important to them to make sure that their water is clean and that they're using the technology that suits their needs and their incoming water qualities. And then it gets a little bit more complicated in some states. Nebraska, where I'm at, Omaha and Lincoln, the bigger cities, have some authority over the approval and design of distribution systems. And so, like, I'm in Lincoln right now, the Lincoln water system can make some small changes to the water distribution system without going up to the Department of Health and Human Services. One way that states can share information is the 10 state standards. The 10 state standards are better for colder regions. So you can see we have a lot more of colder states here. 10 state is usually established technology, and new technology can be acceptable to individual states through the 10 state standards, but the language says it has to be thoroughly tested in a pilot plant for sufficient time, and arrangement must be made so they are protected in case of failure. So this language is pretty vague. It means that Ohio could interpret a sufficient time a lot differently than Pennsylvania. And they're also supposed to account for seasonal fluctuations. Well, what does that mean? That can mean we need to have the coldest temperature and the hottest temperature, or it means like, oh, we need a whole year. So there's a lot of different ways it can be interpreted, and it can still be complicated, even with states in the 10 state standards, to get technology approved. And for example, like Ohio and Pennsylvania might have different steps that they need to go through to get technology approved. And just because something's approved in Ohio doesn't necessarily mean that it's approved in Pennsylvania. So when new technology is approved for drinking water systems, it starts at the state agency. They're the ones that have the authority to approve that new technology. There's a couple different players that might advocate for the approval of a new technology. We have the vendors of the new technology. And as you imagine, they have the most to gain here. They're the ones that can make money off of this new technology. So they're the ones who really want it to be approved by the state agency. And a big hurdle for them is that the state agency is requiring pilot data. And this can cost millions of dollars because the state wants to, the pilot to run a large amount of water to prove that it can hold up to how much water that community is going to need to treat. So large systems play a lot bigger role. A vendor of a new technology might opt to go to a large system, a large city like Chicago or New York, because they're the ones that are going to make the most money off their technology. They're going to make a lot more money off of Chicago than they would from a smaller city like Omaha. And small systems, or like really small systems, don't have a big say in it at all in new technology. Vendors aren't necessarily going to go to a small system and try to get their new technology approved because they just can't make the money. Consultant engineers also play a very small role. Consultant engineers might be more likely to recommend a technology that has been approved for a long time, something that they know is going to work for that system, and they don't want to pay the millions of dollars it might take for that pilot data. So we did a literature review for overall barriers to innovation. We found that limited staff and not enough funding are big barriers. Pilot data, again, using local water quality. So states are really, really looking for their water being tested. They're not necessarily going to take a pilot from a different state. Regulation at the state agency is a barrier to innovation. And then the risk-adverse nature of the water system. So that's that the water systems, they're responsible for making sure water is clean. So they're not necessarily going to take a big risk for fear that it might jeopardize the water supply. Small systems may not have the staff or sufficiently trained staff to monitor technology. And some of these small towns, the the person who's working at the drinking water plant might also work at the wastewater plant, and maybe he mows the baseball fields, or she mows the baseball fields. So they don't have the staff who's dedicated and trained at the small system. And then economy of scale. So like we're talking about with Chicago might be able to afford to pay for that pilot plant, but a smaller system, that would take a large percentage of their budget. And the focus of this study was really these first 4 barriers. So here's the survey that we sent out. It addressed the regulatory barriers. It was sent to all 49 state agencies, and it had 16 questions. It was created through ASDWA, DRISC, and WINS, and was set online in June 2015 to the 49 state agencies. We sent it through ASDWA, hoping that we'd get a better response rate, and we did, 82%, so we were pretty happy with that. Here's the results. So we asked, how often do you consider new technologies for small systems? Kind of an opening, basic question. And we found that new technologies are not frequently considered. So here's frequently at 5%. So the rest, this 95% here, are systems that they're just not considering new technologies for small systems. And again, I don't know if I explained this well, the survey was sent out to the state agencies. So how often are you considering new technologies for small systems? And then how often does your agency's staff have sufficient technical background to evaluate a new technology? So some of these technologies are really new, and the state agency needs someone with a good technical background to ensure that that technology is appropriate for the problem in their state. So a majority of the systems said sometimes, rarely, or never. So they're saying, the majority are saying that we don't really have the sufficient technical background to evaluate all these new technologies. We asked, what are the barriers to acceptance of new technologies? A big barrier is time. So you see our top 2, and with this question, the respondents were able to answer multiple things. So they were able to tick what applied to them. As you can see, 73% are saying staff time per review, limited staff to run the program, and then lack of training for the staff, kind of going back to what we talked about before with the technical background. Surprisingly, lack of funding was not first, but our second most common barrier. So lack of funding for testing, and then concern over cost to the system. So that would be the cost for the actual town to implement the system. And then cost to vendors, not surprisingly, is pretty low. The states aren't as concerned about how much it costs the vendors. Lack of information. Information proved to be a pretty important barrier for these states. Lack of information from vendors, and then lack of support and product for the product. And then surprisingly, procedural and statute were pretty low. So the states are saying that they're not as bogged down by their regulation. It's more information, time, and money. We asked what types of questions need to be answered prior to approving a technology. The biggest thing was pilot data. States really want pilot data from their state with multiple water qualities from multiple locations to support the technology, to prove that that technology will work in their state with their water quality and meet their standards. States are also a little bit concerned about the residuals that might come out of that treatment. Third-party certification was another important one. Where'd my cursor go? There we go. And then we have operator skill to operate. So that's going back to the people who are actually at the small system, not necessarily having a technical background to operate this new technology. Ease of operation, and then actually costs were pretty low. So looking for information about costs. And then vendor contract for replacement was the smallest one. That would be where the vendor would replace the technology if it wasn't working as well as the vendor promised it would. A work group was set up to look through emerging technologies and kind of decide what technologies were considered emerging for small systems. And then the states were given the list and asked to indicate how many times it had been approved. If they had been approved multiple times, a couple times, or if they had evaluated it but not approved it, and then also if they just hadn't looked at it. And we found that some of our technologies that we thought were emerging are actually a little bit more common, like low pressure membranes and high pressure membranes here. We have a lot more approval. There are a lot of locations, a lot of states have approved it at least once. And then it goes down here in descending order of how frequent they've been approved, these technologies. We made some maps to see if we could find any regional trends. And we did find that, again, that some of these technologies are a little bit more widely accepted than we previously thought. So here, dark blue is approved the technology at least once. Light blue is evaluated the technology but did not grant approval. And white is never evaluated the technology. And horizontal lines did not respond to survey. So you can see here with my 10-state standards example, you can see that Ohio has approved this at least once, but even though Pennsylvania is in the 10 states, they haven't even evaluated this technology for in-distribution aeration of disinfection byproduct removal. And the reason why these maps could be helpful is that states don't necessarily know what other states have approved a technology. So if I'm here in Nebraska, and I'm thinking about UV medium pressure, I could call my friends in Iowa and say, hey, I see that you've approved this technology. Can I see your pilot data? What kind of problems have you run into? Why do you like it? But I could also call my friends in Colorado and ask them, well, why didn't you approve it? You looked at this technology, but you didn't approve it. So I'm curious what sort of problems you saw with it. We asked about ETV certification. The Environmental Technology Verification Program, it provided credible data for 500 technologies. So it could be a very useful program for if we're looking at a technology that's going to be approved. It had protocols, test plans, reports, and verification summaries that could be really helpful to state agencies. And we asked if the states rely on ETV certification. About a half said yes, about a third said no, and about a fifth said that they weren't even aware of the program. So there's some proposed information sharing networks. We really found that there is information out there about these new technologies, and states just need to have a way that they can share that information. So a website, developing common standards so that it makes it easier for technologies to be approved, and then partner for approval. That would be if two states work together, and if one state approves that, then another state would automatically approve that technology. We found that states were pretty interested in information sharing. Only, I think, one had no interest. And then develop common standards and partner for approval were also pretty popular. So conclusions, approval of new technologies is really complicated in our federal system. And small systems do face different challenges. And technology isn't frequently considered for small systems. Limited staff, data, and training are barriers to innovation. And acceptance for new technologies varies from state to state, and states are interested in sharing data. Here's some recommendations. I'll go through that because we're running a long time. So I'd like to thank Bruce Dvorak, my advisor, and Steve Wilson from the University of Illinois. They did a lot to set up the survey kind of before I joined the university. If you're looking for more information, we did have a paper on this topic published in the Journal American Water Works Association. Here's the title and the DOI. If you're really looking for more information, you can download my thesis on Digital Commons, and that has all of the questions that we asked with all the responses, and it's more in depth. All right, questions?
Well, thank you, Deanna, for that awesome presentation. I work for Steve Wilson too, and I know he has he's done a survey for getting innovative technologies approved as well. And I've seen other presentations, like for example, like getting UV technology involved. And a lot of people say, yeah, like they don't have any money. The states they don't have the manpower to do the pilot data. So it's pretty interesting to see what your data showed.
Yeah, thanks.
And to start off our question, we have one question. Do you know much about approval protocols for point of use or point of entry technologies?
I know that it varies from state to state, like all the other ones. Um, and that's about all I could tell you. Sorry. This was a long time ago, and I'm currently pregnant, so my brain doesn't always work in the afternoons.
No problem. It's hard because you have to monitor 49 states, and every state has different protocols for approving stuff. So I'm guessing
Exactly.
it's best to just contact the state agency for more information. Did you have any problems getting information from state agencies? I know, I forgot what the exact numbers were, but some of the agencies didn't respond back to you. But were most of the state agencies pretty? Were they willing to help you out, present information? Because I was under the impression that most states didn't want to share their pilot data information.
Yeah, well, we didn't get any actual pilot data information from the states, but as far as returning the survey, we had a pretty good response. And I think part of that was using ASDOA because it's a professional organization that these state agencies are familiar with.
Mm-hmm.
And yeah, we did have a couple that returned back anonymous. But for the most part, it was pretty successful. And there was a couple things I had to contact the state agencies for just for clarification on their answers. And everybody that I talked to was pretty helpful. But I work for a state agency now, so I'm going to tell you that we're all really nice.
Awesome, thank you. I think that's all the questions we have for now. So we will be switching our presenter to Nicholas. Let's go here. All right, so our next presenter is Nicholas, who will be discussing his research on monitoring disinfection byproducts at a full-scale drinking water treatment plant and evaluating data to predict DBP occurrence. Nicholas, whenever you're free, please start.
Yes, thank you. Is everybody seeing the slides? I guess so. All right. Anyways, so this is a presentation I adapted from what I presented last month in the Water Quality Technology Conference in Portland, Oregon. It's related to my my PhD work. So this is basically the first step, first sampling campaign I did as part of my PhD. So the focus here is going to be much more technical and much more small scale than the previous presentation. So we're going to look at DBPs in a full-scale drinking water treatment plant. And I'm going to go mostly over occurrence of the DBPs and differential UV absorbance monitoring to predict the DBP concentrations. The reaction rates I'll go quickly over because I had to shorten the presentation because it was originally a 30-minute presentation. So basically, in the province of Quebec, we have THM and HAA standards similar to what you have guys in the US. And in some municipalities, the THM standards are not always met, mostly due to summer samples. So what we wanted to do was to give the plant we work with some frequent feedback on DBPs so they could know when they did well and when they did not so well, and eventually adjust their operation to minimize the DBP concentrations in the summer. So the plant was not really a medium-sized plant. We'll see it a bit later. It was not a small system, sorry. It's more of a medium system. But the technology we're looking at, differential UV absorbance, could possibly be applicable to small systems. So hence the interest here. So our objective for this the sampling campaigns we did was to characterize the formation of DBPs, and we looked at the regulated DBPs and also 3 families of unregulated DBPs, so chloropicrin, haloacetonitrils, HANs, and haloketones, HKs. So we compared the 2 types of model, the kinetic model with the reaction rates and the differential UV absorbance to predict the DBP concentrations and evaluate the potential. It is actually the first time we evaluate the potential of differential UV in full-scale conditions. So our case study is located in the province of Quebec. So for those who've been here, it's close to Montreal, about an hour north, and it takes its water from the North River. It's simply called North River. It's a rather clean water, so it doesn't have too much organic matter in there. So the plant is not so small. As I said, it's a medium-sized plant, and it has a conventional treatment, so coagulation, flocculation, filtration, followed by disinfection. And it has, as you can see, sodium hypochlorite disinfection and chlorine dioxide and UV reactors. So it has 3 types of disinfection. So our sampling campaign was designed to follow the water from the raw water intake to the plant. So we evaluate approximated travel time of the water through the different treatment processes, and we followed the water from its entrance to the exit of the plant. We sampled a bunch of parameters, the typical physical-chemical parameters. We measured UV absorbance between 200 and 350 nanometers. And of course, we measured the DBPs that we're interested in. The kinetic model we calibrated is the one for chlorine decay, is the one proposed by Haas and Kara. So a parallel 2-phase first order decay. So a rapid phase, so fraction X of the chlorine degrades rapidly, and the other fraction degrades slowly with a slower reaction rate. And the DBP formation basically builds on that with a formation rate for the rapid formation of DBP and a slow formation rate for the slow fraction of the chlorine decay. So the K1 and K2 comes from the first model, and the K1A and K2A are calibrated for each DBP. The differential absorbance model, so it's much simpler. It consists in measuring UV absorbance before chlorination and then at any time or any time, any temperature, any pH after chlorination. And the difference between the two absorbance can be related to the concentration of DBP. So we calibrated these models using a simple linear model. Other types of curves have been proposed, but really it does barely improve the fit here, so we stayed with the most simple model. So here you can see the results for THM concentrations. The results show that basically in all seasons except summer, the results were pretty low, below 40. And in the summer, during the data we sampled, the results show that we reached about 50, I think it was 48 or 49 micrograms per liter of total THMs. And for the HAAs, same thing. So of course, the summer campaign, the campaign we did in July, we sampled more HAAs. Although there are more variability between the three other campaigns in this case. The unregulated DBP, the chloropicrin behave somehow like THM. So basically, there's a rapid formation and then there's a slower formation afterwards. While total HAN and total HK behave a bit differently. So in the winter, you have the rapid and slow formation phase, but in the July campaign, in the summer when the water is warm, you can observe degradation for both THN and THKs, which means basically the important season for these two families of DBPs is not the summer as it is for other DBPs, but mostly winter or maybe spring or fall would be the seasons where you need to be careful about the concentration of these DBPs. As I said, I will not go through all these details. What you need to see here is that the determination coefficients for the chlorine concentration model was very, very good. So it's very easy to retrofit these models. However, it's a bit harder to predict the parameters, so the reaction rates K1 and K2, and the rapid and slowly decaying fractions. We weren't able actually to predict them. We're just able to back calculate them basically. So here's an example of what it looks like. The red dots are chlorine dioxide interference, because we only measured chlorine residuals using the DPD method, and the chlorine dioxide interferes. So where the chlorine dioxide is dosed, we could not get the exact chlorine measurement. And when you look at the THM and HAA models built on that, you can see that the determination coefficients are also quite good, and that the reaction rates are higher in the summer and in fall when you get most of your natural organic matter. So this is all logical, and again, the hard thing was to predict the reaction rates. It's very easy to back calculate them, not so much to predict them. So here again, an example of the results. Differential UV model now. So this is an example of what you get when you measure UV between 200 nanometer and 350. And this is directly not a UV measurement, but a differential UV spectra. So we've taken UV before chlorination and then at different times after chlorination, and we subtracted one from the other and obtained the spectra. The good news is there's a peak around 270 nanometer, which is usually what is expected. In the literature, we find a peak at 272. And the differential UV absorbance is increasing with time, which is also another good news, because that's what we expect. The problem is when we look at the prediction, what we find is that the slopes of the regression, linear regressions, vary from one campaign to the other, and mostly the intercept also vary. This was kind of expected in the literature, although it's the first time that it's been shown. So what it means is we need either to be able to predict them, or otherwise it's going to be much harder to predict the DBPs if we don't know, because I don't show it here, but if you put all the data together, the determination coefficient would be about 0.4, which is not as high as what we get when we don't pool the data from the different campaigns together. One of the interesting results is the positive intercept in the summer, very positive. You would expect that some absorbance will be destroyed before you get any DBPs measurable, but in this case, it is as if before you even chlorinate, you have DBPs, which was not the case. We verified it. There was no DBP in the raw water. There is no water recirculated in the plant, so it was not possible. So it probably has to do with either precursors that do not absorb UV, or particulate matter that produce DBPs, and that of course do not absorb UV either. So yeah, just a simple comparison with a few of the previous literature. The intercept was always negative, so all of the lines here would go here. So we know that basically you need to destroy some UV before you can measure some DBPs. So here are a bit of the conclusions from the study. So yeah, basically for DBP occurrence, nothing new, nothing that wasn't known from the literature was found. That was not the point of the research. For the kinetic model, we have excellent prediction performance, but as I said, the parameters were very difficult to predict. In the original publication that suggested these models, they had equations to predict the parameters, but they didn't fit our water at all. The predictions were like determination coefficients of 0.1, 0.05, something like that. So it didn't work at all. The differential UV absorbance is the most interesting, or the most the most interesting technique in our opinion. It allows for good prediction nonetheless, with really two measures, absorbance before and absorbance after chlorination. So it's a very, very simple technique. So that's the reason why it could be applied. And even now with continuous UV monitoring, UV probes that are available, it could be automated basically and incorporated into a SCADA. So that's interesting, although there are still some problems, some issues that need to be resolved before very good predictions can be attained, especially the question of the positive intercept and of the variation of the regression from one period to another. So yeah, this is a question that has to be raised. Will the model hold true from 1 week, from 1 day, from 1 month to another? That's a very good question. And yeah, to conclude more philosophically, even though it's not that precise so far, it has kind of a certain, we can still improve the technique. You still have to ask yourself, how precise of a feedback do you need when it's only for operation? Of course, this is not for regulatory compliance, but if it's only for operation, even if you have a 10 or 20 or 25% uncertainty on your result, it can still tell you if you are close to the regulatory barrier, or if you're much over the barrier, or much under the regulatory standard. So it can still be a very valuable information to have, even though it's still not precise at that point in the development of the technology. So I'd like to acknowledge a few people. A lot of students at the research chair at Laval University helped us in the sampling campaigns, and of course the NSERC that funded the research, and all the staff at the treatment plant provided a lot of help during these campaigns. So yes, I'd like to thank them. Is there any questions?
Well, Nicolas, thank you for your interesting presentation. I was actually in Portland as well for the conference, but I suppose I missed your presentation, or I didn't get the chance to see your presentation. So to start with our question, and for your the graphs you showed earlier of the for each DBPs in each month, you showed the total HK had a rapid digression for the graph, and I was wondering, do you have an explanation for why specifically that one had the most significant decline compared to the other DBPs?
Well, yes, actually, we did not find this. That has been found before in the literature. HKs, so the total HK is actually the sum of dichloropropane and trichloropropane, and they both degrade quite fast at pH over 7. And in this case, the pH in the reaction tank is about 8. So yeah, that's basically the reason why it degrades. It is the same pH in the March campaign, but because of lower temperature, it's a much lower kinetic rate, and we kind of see a degradation starting, but this could only be due to uncertainty on the measurements also. So what we really see is high temperatures combined with high pH produces this.
Interesting. And was this study done at a relatively large scale treatment facility, or was it a small treatment facility?
It's kind of a medium-sized plant, so the average flow rate is 170 million gallons per day. So that gives a hint.
Right. Well, I've never seen like or at least for a small facility that use. I guess this is 3 steps of disinfection, right? Using sodium chloride and CO2 and a UV reactor.
I'm sorry, I didn't get a question.
This was it's a 3-step disinfection process, right?
Well, kind of. The chlorine dioxide really is there only for oxidation purposes, so they don't get any disinfection credit from it.
Mm-hmm.
So they only added it a few years later after they had THM problems, so they wanted to lower the THM, so they added this. It oxidizes organic matter. It also oxidizes the remaining iron, manganese. So it does disinfect, but it's not used as a disinfectant really here.
I see. Do you plan on doing a similar test at a different facility, or are you just going to stay at this certain facility and keep on doing more tests?
It is being tested right now. So the differential UV absorbance technique is being tested in a facility that is partner of the research chair also, although I'm not the one analyzing the data. So it's a postdoc from our university who's doing it right now.
I see. Well, that's all the questions we have for now. So I think we will be concluding our session for today. I would like to thank both of our presenters for their presentation. And again, if anyone missed it, this is being recorded and will be posted on the Drinking Water Center's website after this presentation will be over. So once again, thank you very much for our presenters, and thank you for everyone for attending.
Thank you.